We're going to look at 3.1 day 2. First, let's look at correlation. So the symbol for correlation is a lowercase r. It also is in our calculator. And then the formula is on the formula sheet. It's a fairly involved formula, but it's not critical for you to memorize that. So what correlation does is it measures the direction and strength of the linear relationship between the two quantitative variables. R can be as small as -1 or as big as 1. It can't be outside those two values. So the closer to 1 or -1, the more linear the relationship, thus the stronger the strength, right? The points are more closely together and appear to be more linear than as it gets closer and closer to 0, where there becomes to be more and more scattering of the points, thus a weaker relationship. Facts about correlation. So we want to make sure that we write, on number 9, it says describe the direction, strength, and two variables. So when A is equal to 1, it's positive and strong. When -1, when R is equal to -1, it's negative and strong. And then when it's 0, there's really no, it's not positive or it's negative, there's really no correlation. It's just kind of like a horizontal line. Think of something like no slope. All right, so facts about correlation. So first, correlation makes no distinction between explanatory and response variables. So whereas we always want to put the explanatory on the x-axis and the response on the y-axis, the correlation will actually be the same no matter what, where you have what variables. So the second thing is R, the correlation, right? R does not change when we change the units of measurement. That's because R doesn't have any units of measurement. They cancel each other out in the formula, so R is just a number. And then that's what the next part is. So correlation, R itself, has no unit of measurement. It's just a number. The measurement from the x and y variables actually cancel out each other in the formula because you take the difference in the x's and the x minus x's mean, and you divide it by x's standard deviation, which cancels out all of the units. So correlation doesn't have any units itself. All right, so next, regarding correlation, this requires that both variables be quantitative. If you don't have quantitative variables, then you don't have a scatter plot. All right. You can actually find a value of correlation for any scatter plot, but R only works with or works for linear relationships. So what actually is true is that something in the shape of a parabola also has R equals 1, but that doesn't show any sort of relationship between the two. It's just something that happens to be true. So we want to always make sure that the graph is linear. So R measures only linear relationships. So you always have to make sure that you check to make sure that the graph is linear. So while this is true, the fact of what R does doesn't help us in a nonlinear environment. All right, the third thing is that correlation is not resistant to outliers. So basically it's affected just in the same way that mean is. And then fourth, a correlation does not give us a complete summary. It just shows us that there's a relationship between the two variables. It doesn't tell us that there's causation between the two because we don't know anything about lurking variables that might not be evident on the graph. All right, and then chapter 1 dealt with one variable, which data is what goes in those blanks. This chapter deals with describing two quantitative variables, and we call this bivariate data. So this is the mantra for describing data. Anytime you have a problem that talks about describing data, or if you have a scatter plot, somewhere on there you need to write the sentence. So basically there is a strong or moderately weak, negative or positive, linear or nonlinear association between whatever the explanatory variable is and the response variable. So this is something that you'll want to make sure that you memorize because this will be important. So number 10, we are going to do that problem tomorrow in class. It's kind of involved and it's a little bit different with the positive and negative values, so I don't want you to get confused. So let's go ahead and skip to number 11. So number 11 asks us to rank the correlations and the problems from least correlation to most correlation or highest correlation. So the three things are the heights of fathers and their sons, the heights of husbands and wives, and the heights of women at 4 and at 18. So the lowest is probably pretty evident. It's the husbands and wives. So there's really not a strong correlation between the height of a husband and his wife. The middle one is the fathers and son. There is some correlation, right? If your dad's tall, then you yourself might be tall. But then again, you know, my dad has a brother that's 6 foot, and his dad was about 6 foot, but my dad's only 5'5", so not always true. So that's why there's a little bit of a scattering of the points. And then the highest would be the women age 4 and 18. Usually when you're 4, it kind of predicts your height of what you'll be when you're 18. So now let's look at number 12. So number 12 already has all the data graphed for you, and this is about the comparison between body weight and brain weight in mammals. So the correlation between body weight and brain weight is R equals 0.86. So that's pretty close to 1. So this is going to be fairly strong. All right. So let's go ahead and write our sentence. So there is a fairly strong, we could also say strong, a fairly strong, all right, we look at the association, it's positive, it's going uphill from left to right, and it appears to be pretty linear. I mean, there's some points here, the dolphin and the human and the hippo are kind of scattering from each other, but other than that, it's pretty linear. A fairly strong, positive, linear association between, now we're going to say the X variable, so the body weight, and we're going to say the Y variable, brain weight of mammals, the context. All right, so that kind of follows that mantra. What effect would removing the elephant have on the correlation? So if we took this elephant away, this line would not go near that high. It would be more like in here, kind of a little bit less steep, which means the correlation right there, this point wouldn't be pulling the line towards it. So the correlation, these guys would have more scattering here, be less linear. So the correlation would decrease. because there would be more scattering of points. Okay, so let's look at number 13. So I want you to try and make the graph on your own on 13, plugging the information in your calculator like I showed you how to do yesterday, and then make a scatter plot. So pause the video, do this, and then when you're done, let's go ahead and restart the video and make sure that you know what you're doing. So go ahead and pause it. So hopefully you actually did what I asked and you have the graph in front of you. So I graphed mine on my paper and then took a picture of it, so hopefully you can see kind of what's going on. And then it asks us to describe the distribution. So there is and you can see that these points are not too bad. I mean, they're kind of a little bit of a scattering, but they have some sort of a linear motion. But they are, I mean, they're not close together is what I'm trying to say. So we're going to call that a moderately weak. All right, it's still positive. Plus, the other thing is, because we put in our calculator, we can always look at R and see what it is. Linear association between the X variable, so height of women, and the Y variable, height of men. And go, done. So let's go to part A. Or part B, I guess. How would R change if all men were 6 inches shorter? So basically, if we took everything and subtracted 6 from it, would R change? And the answer is no. R would not change. All right? And then it says, does the correlation tell us if women tend to date men taller than themselves? All right, so we can't exactly make that causation, but we can see that as the women get taller, right? If you look at like 66, 70, those women, they tend to date men that are taller than them. So taller women tend to date taller men. So it's not exactly a really good question on there because the correlation is so weak, but this is the answer that was in the book. I probably would have said that there does appear to be that women do tend to date men that are taller than themselves. Part C says, if heights were measured in centimeters rather than inches, would the correlation change? No. Units do not affect correlation. Right? So any change in units doesn't matter. It doesn't have any effect on it. If X and Y variables are reversed, how would the correlation change? It wouldn't. Correlation makes no distinction between explanatory and response variables. All right, so tomorrow we'll do the problem that we skipped, and then just in case you're not going to be in class tomorrow, the assignment's there. It's on page 160, and we'll do those problems. And we will have the take-home quiz tomorrow. So again, if you're absent tomorrow, you'll want to stop by and get that take-home quiz.